Hello everybody, Mr. Klein back. Today we're going to talk about lesson 1-2, the derivative. You might have heard this word before, the derivative. It is half of calculus, these ideas of the derivative. We're going to talk about it today. Now, in our last lesson, we talked about something else called an instantaneous rate of change. And an instantaneous rate of change is when you have an object and it's in motion, at a particular instant along its path, how fast it's moving is its instantaneous rate of change. Well, guess what? The derivative is the instantaneous rate of change. That's it. Let's write it down. I'm going to give you a definition. You want to know this one. Okay, so first thing, the derivative of, when I write f of x, you want to think a function at, and when I write x equals c, this refers to at some point. C is for constant. So say this aloud to yourself, the derivative of a function at a point. Go on, actually say it. You say it right now. The derivative of a function at a point is the instantaneous rate at which f of x changes at x equals c. Now, why do we call it the derivative rather than the instantaneous rate of change? Why have two words? I think part of it's because we're lazy. It's easier to say the derivative. And it would be even easier if we had like a nice little symbol. So in fact, here's how lazy we are. We write it as that right there. When you see that little hash mark, maybe you've seen that before. That hash mark is referring to the fact that we want the derivative or the instantaneous rate of change. Also, we would refer to this as a prime. So you'll hear me call this f prime of c. Okay, so with that in mind, now that we know a little notation and we know what a derivative is, there are three, count them three, 1, 2, 3 ways that we can calculate the derivative. Let's talk about each one. Option number 1 goes like this. Suppose that we are given a graphical representation. So I'm going to draw a little graph. You draw it too. Let's go. Okay, so here's a graph of a function. You might have seen functions that look like this before. What would you call a function that looks like this? If you were thinking to yourself, a parabola, you're right. If you were thinking to yourself, a quadratic, you are also right. If you were thinking to yourself, I would call this a pentagon, you are incorrect. I want to calculate this right here. I want to approximate so this says state the instantaneous rate of change of this function f at time 1, or when x is equal to 1. So first we would calculate where x is, or we would identify where x is 1. That would be right here. Now, we kind of talked about this in our last lesson, that the way we can identify the instantaneous rate of change from a graph is to look at the slope at that instant. So as you're looking at this, notice that we have these positive slopes over here on the left, and then the slope is 0 for an instant right here. And then when we get to this point right here, the slope is negative. Now, you don't have to do this perfectly, but I'd like you to try to be as accurate as you can. Try to line up the straight edge so that it comes nice and close to that point. So there's my line. Next thing we're going to do is we're just going to calculate the slope working with what we've got here. So we know from our time back in, say, the 8th or 9th grade, that a slope is the amount of change that you have in y for a given change in x. And so on this line right here, I'm going to look at the change in y and the change in x. And that just means I need to pick 2 points. I'm going to pick, say, this is my second point. I'm going to look at, there's my change in y. There's my change in x. Now, I chose that point strategically because I think it's nice and easy here to have a change in x of 1. And to accompany that change in x of 1, here we have a change in y. And if you said that this change in y is 2, get out of here. You're wrong. Because notice that the line went down by 2, which means this should be a negative 2. And so my estimate of the derivative at 1 is going to be our change in y is negative 2. Our change in x is 1. That gives me negative 2. All right. If I want to write down the steps here, I think we would say step 1 is draw a tangent line. And step 2 is to estimate the change in the y value for a given change in the x value. Let's see. So that's the graphical method. I promised you guys 3 methods, so let's look at another one. Second one is what I'm going to call the table method. Your book will refer to this as numerical. All right, and so I need to give you a table. Let's do a table that looks something like this. X, f of x. Let's pick some x values. Let's go 0, 1, 2, 3, 4. And let's do some y values. Let's go 5, 4, 1, negative 4, negative 11. And let's do the same thing we did in the last one. I want you to approximate the instantaneous rate of change at 1. Now, just like we did before, you've got 2 points and you're going to find the slope between them. So you're definitely going to do something that looks like this. Change in y, change in x. But here's the thing, we've got 1, 2, 3, 4, 5 points. Which of those 5 points should we use to find our slope based on the fact that we want the instantaneous rate of change at 1? Should we pick these 2? Should we pick these 2? Could we have some other option? Now, it might be tempting to pick this one and this one. And that would be an okay estimate, but it wouldn't be the best one. And it might also be tempting to pick this one and this one. That would also be an okay estimate, but not the best one. The best estimate is to pick one that is smaller and one that is larger than the value you're trying to estimate. So since I wanted the rate at 1, I picked this one and this one. And let me show you why I do that. I don't know if you noticed, but these numbers come from this graph. Now, if you picked the first 2 values, 0 and 1, you were finding the slope right here. And I can't help but notice that that is less steep than what we actually want. And if you picked the numbers 1 and 2, that means that you were finding this slope right here. And I can't help but notice that that slope is too big. But if you picked 0 and you picked 2, so two numbers on either side of the point we're trying to estimate, you notice that this is just about right. And in fact, check it out. Come back down here. This would be our change in x. So our change in x would be equal to 2. This is our change in y. Y went from 5 down to 1, so that would be a change in y of -4. I guess I will write those out over here just because I've already got it set up. 0 and 2. The 2 goes with the 1. The 5 goes with the 0. That would give us -4 over 2, which gives us -2, which, what do you know, is the exact same answer that we got right here. I like it. All right. So the moral of the story is that anytime you're working with a table, you're going to pick one value that's smaller and one that is larger. This has a name. This is called a symmetric difference quotient. Now you look like you are a smart little cookie. So I'm guessing that you're looking at these words and those are kind of making sense to you. You're saying to yourself, okay, I get it. This is a difference, subtraction. And the bar right here, that's a quotient, division. And symmetric is like symmetry. We are having symmetry about 1 because we picked a value that was below and then an equal distance above. So this is called a symmetric difference quotient. Good stuff. Come along with me to the last method of calculating the derivative. And this is when you are given an equation. Your book also refers to this as a numerical method. All right. So that equation that I gave you here and here, well, I didn't give you the equation, but I gave you the graph, and then I gave you the table. The equation that goes with it is f of x is equal to 5 take away x squared. Right? And let's suppose that we want to approximate the instantaneous rate of change at 1, or the derivative at 1. We already learned this, right? We learned that you can use that as your rule, you're going to use as your tolerance, the change in x is equal to 0.001. Okay, and so what I want to show you how to do, since you already know that, I want to show you how to do this on a calculator and make your life a little bit easier. Okay, so first let's write it out. F prime of 1 would be approximately, 1 goes here, 0.001 larger than 1 goes here. The value of the function at 1 goes right here, and the value of the function at 1.001 goes right here. All right, so that's what we're going to plug into the calculator. Now, to save us a little bit of work, let me show you a little bit of, let me show you a couple tricks on this thing. All right, so you got your calculator out. In your calculator here under y1, I want you to type in the function. And then the first thing I want to show you is that if you hit alpha trace, there's a menu that will show up. And since we just typed our equation into y1, I want you to select y1. And then let's suppose I wanted the value of y1 at 1.001. All I would have to do is type in that instruction and there we go, right? Okay, so very useful. If that didn't work, if the second trace didn't, the alpha trace didn't give you what you wanted, there's another option. It's this. You can hit vars. Vars is for variables, and then you can go to y vars, and you can pick function, and then you can choose y1, and that will do the exact same thing for you. Okay. Now, it might be helpful to do this. I'm going to type the entire numerator. So I'm going to go alpha trace minus alpha trace. So that tells me what the numerator is going to be, right? Okay, so that's pretty useful. I might even go so far as to do this. I might go parenthesis and then come back up here. So the cursor's up here, and then hit enter. And then parenthesis again, so that I've trapped the entire numerator, and now I can divide it by the denominator, which is 1.001 minus 1. One thing I want to emphasize to you guys is that this is not going to work if you don't use the parentheses. Anyway, by doing that, ba-boom, I got myself my answer. And take a look at that. It is negative 2.001, which makes sense because all the answers we've been getting were around negative 2. All right, so that's the moral of the story, folks. You know what the derivative is. You know how to calculate it if you have a graph, if you have a table, and if you have an equation. Good day.